In this video, we're going to take a look at how software communicates with hardware in your machine. Now, you may remember last week we did an experiment in our assignment with a CPU, and we saw that a CPU had several registers in it. And these registers were sort of a scratch pad, if you will, a working area where the CPU could do its calculations, right? You'd put a number in one of the registers, and then you put another number in another register, and then you do it, say, an addition or a subtraction or a multiplication, and you put the result in another register, and then you could move that in and out of memory. We didn't look at the fact that you could also move that to a device in your machine. But surprisingly, most communication with devices is not done that way. It's actually done directly to the device. Now, the CPU still has a role in that. It still has to conduct the ability and the capability, and I should say the permissions to access that device. But the transfer itself, all of that data moving from one place to another, doesn't have to go through the CPU. That frees up the CPU to do other kinds of things and do the heavy lifting. So once it allows this transfer, let's say we want to transfer a bunch of data from a disk drive into memory, for example, that can just go directly from the disk drive into those memory slots without all of that data having to go through the CPU. That saves a lot of time and a lot of work on the CPU. What you're looking at here in this slide is a set of registers that are not on the CPU but are on the device itself. So in this case, we're looking at a register that is a storage location that is on the I/O device, not in the CPU. Now, there is also an I/O controller, and that I/O controller is also on the device itself. If you were to take a hard drive, for example, an old magnetic hard drive, and take the covers off, you would not only see the wheel, the disk that holds the data, you would also see a card in there, an electronic card that has a bunch of electronics on it, a bunch of chips on it, and part of what that is the I/O controller. And also the registers, the memory, so that we can move information directly from memory to that device. And so that I/O controller controls that information. There's also a control register, which is where the device driver writes commands. So in other words, there's also an area where commands go, just like we saw last week with the CPU, where we send commands to the CPU. In this case, we're sending commands to this device. It's kind of a little mini CPU on that device itself. There's a data register where the device driver writes the data that the device outputs and reads data that the device inputs. So there, as you can see, it's going to go into the register, into the data register via the I/O controller, and then be stored or calculated or whatever it needs to be done, right, using this register, using the storage register, which then allows it to be written directly onto that device. So that's kind of how that works. Now, there's also a status register, just like we saw on the CPU. You may remember on the CPU we had a register that kept track of where things are. In other words, where the next location is, or where the next location of the next command is. We have something similar on the device that tells the device where it's at, what it's doing, what its status is, and so we have a status register on the device itself. Now, here's some information about how big those things are. Most of these are 2 to 4 bytes long, and that's just some trivia information. How long the data registers, how big a chunk of information data registers can handle, 2 to 4 bytes. And a byte, you remember, is 8 bits. So 4 bytes, for example, would be 32 bits. There is also another chip that is on that control board that's on a device called a FIFO chip, first in, first out, which allows, or I should say controls, the order in which information is written in and out of that device. Now, one thing you might want to notice on this slide is the lack of something. not what's here, but what's not here. Notice what's not here. There's no CPU. So here in our Word document, we want to write to this disk drive. So we send a request to the operating system. Now the device driver is part of the operating system. It may be built into the kernel of the operating system, or it may be a device driver that we have added onto the operating system. Whenever you include a device driver, or you install a device driver, it's like adding a module onto the kernel of the operating system. And so that is, I like to think of it as, let me see if I can draw this here. Take a pen. I like to think of it like this. So here is the kernel, right? And part of this kernel has the device drivers. I'm drawing this with my mouse here. And then when I install a device driver, right, it adds that installed device driver here, and I add some more here. So I'm actually expanding the kernel itself, or this device driver portion of the kernel itself. So device drivers are, you can think of them as extensions of the kernel, or of the heart of the operating system. So we're actually, when we say device driver, we're actually talking about the operating system here, not the CPU. And then from this device driver, or from the operating system, we go directly over here to this disk drive. So notice that there is no CPU here, right? No CPU. And so that's the whole point of this section, is the fact that our I/O device communication often bypasses the CPU. Over here we want to see how that works. In other words, how is that accomplished? And there are a couple of ways that we can do it. We can either map the device through ports or through memory. Now, many devices are what we call memory mapped. I remember on the very first computer I ever had was many years ago, the old Radio Shack TRS-80 computer, and the monitor was memory mapped, so that all I had to do was put a piece of information, which I could do programmatically. I could poke, they called it peek and poke. I could poke a number into a memory location, and it would show up on the monitor, on the screen, as a letter or a block or a symbol or whatever it was that I put in there, depending on the number I put in it. So it was just a part of memory. You could think of the screen as a window into that part of memory. We don't do that way anymore, but that would be a memory mapped device. We still have lots of memory mapped devices. So let me show you here. For example, I'm going to go to the device manager, and let's go down to let's go to security devices. And I'm going to look at the TPM, a trusted platform module, which is a chip on my motherboard. And I'm going to go down to the properties and over to the resources. These are the resources on my computer that it uses. And you'll see that it's using memory, a certain memory range. So it has control of this part of memory. And I can't use this part of memory for anything else. And so the TPM is memory mapped to this part of my memory. It can also be mapped to ports, and often you'll see, for example, USB ports or printer ports. All the ports that are on your computer itself, the physical ports, are often mapped to what we call logical ports on the system. Let me go back to Disk Manager again, and I will look at the ports. Okay, so right now I've got Bluetooth radio controllers on several ports. It looks like I have several Bluetooth controllers on here, on COM3, COM4, COM5, COM7. The LPT ports are used for printers. On some computers, if I plug something into one of the USB ports, that will also show up here as a port, as a COM port. So many things actually communicate through these ports, and these are the logical port numbers that I'm talking about that show up over here, rather than memory. They show up on these ports. So those are two different ways that we can communicate, through the port or through memory. In this section, we're looking at programmed I/O versus direct memory access. Now, what does this mean? I said that we often bypass the CPU. Well, there are a couple of ways that we can bypass CPU. We can use the DMA, and that's down. This is actually the second section down here, the DMA controller. Now, DMA means direct memory access. In other words, I can use the memory of the machine and go direct from device to device. Let's say from memory to a device without going through the CPU. And this actually is not as popular as it once was. Usually storage devices, networking devices often used direct memory access. Today we have other ways of doing this that are a little bit more advanced, and we're not going to go into those methods. Although I will mention the terminology. The way that we often do it today is something called bus mastering, and it's not quite as easy to see when bus mastering is happening. That would be the second way. This is the first way, and the second way is not on here. I'm not going to try to write this with my mouse, but I'll just put B and then M for bus mastering, which would be the second big way that we bypass it. Now, if we're not bypassing the CPU, then we're doing something called programmed I/O or PIO. That's where we actually do require the CPU and go through the CPU rather than bypassing the CPU. So this winds up this section on I/O communication. I hope I clarified the meaning of this a little bit and helped a little bit. It can be a little bit confusing.